My name is Daniel Schaudt, and I'm a researcher at the Technische Hochschule Ulm, and I'm here with my supervisor, Professor Reinhold von Schwerin. And as you can see from the logos on top, this is a cooperating research project between the Technische Hochschule Ulm and the Uniklinik Ulm. And so I would like to thank the colleagues and doctors and radiologists from the Uniklinik Ulm, Professor Meinrad Beer, Dr. Christopher Claude, and Andreas Hinteregger for providing the data for this study. And last but not least, I want to thank Christian Späth, who is not here. He did his master's thesis on the subject of actually generating the synthetic images, so credit goes to him here as well. All right, so I'm referring to improving COVID-19 X-ray, chest X-ray image detection with synthetic data augmentation. So we are obviously building a COVID-19 chest X-ray detector based on deep learning, of course. So I'm posing the question for a start, why is this even a good idea? And the reason is the tests that are usually being done for COVID-19 are the PCR tests that you all know probably, and they have a rather high false negative rate, and they take a long time to be done. So the X-ray images would be a fast and easy to obtain alternative. And there's another very important advantage of using X-rays for this, and this would be that we have no need for a specialized medical staff, because this is especially true in an emergency setting where the model would be very helpful. If the patient comes in at the emergency room at 3 a.m. in the morning and has some respiratory illness, you can get a very fast screening, and it's also a very fast first-line triage tool for doctors. So it's a good idea to do this. So we got some data, of course. Lung X-ray images, as I said, from the first wave of COVID in the Uniklinik Ulm. And we do see on the left-hand side we have COVID-19 positives and negatives. For the positive images you see in blue, like the typical ground glass opacities that you see as infiltrates in the lungs. I'm not a doctor myself, so I can only explain it as a white shadow being seen in the lung, but you actually need a lot of training to see this. And this is one of the problems for deep learning here. It's an actual hard problem to solve. And the second problem is, as you can see, the study data is very small. So we have 110 positive images and 223 negative ones. And for deep learning, this is basically nothing. So what did we do? There are some possible solutions to this sparse data domain, and you have all heard some of them. And I'm just iterating over through them real quick. Transfer learning, of course, we're doing this. But as you can see, like the ImageNet image space is pretty different to our image space. So it's very monochrome, and it is very, very narrow in this sense. And we're still using transfer learning, and we think it's a good tool, but there's still a question if this is even, if this makes sense in the grand scheme of things. So the second thing we do is data augmentation. But also we have here a problem that you usually are not getting everywhere, which is if you're using some of the most commonly used data augmentation tools, like the horizontal flip that you see here, for the lung X-ray images, that could be a problem because all of a sudden the organs are on the wrong side of the image, right? So you have all of a sudden you are introducing a medical condition to this, like the situs inversus, where the organs are on the wrong side. So that's not what you want to have, actually. And this is the same thing for color jittering. So every color manipulating data augmentation could be a problem, because when you are getting X-rays that are all of a sudden pink, it just doesn't make sense. Okay, third option, synthetic images. So we thought, well, we could just use this as a fancy data augmentation tool and generate our own synthetic images, and that's what we did. So we still don't have a lot of data here. And we thought, okay, we use this opportunity to get a very clean data set from the Uniklinik Ulm and use some openly available data that you can find online. There have been put together very good data sets for COVID detection, and we are using one of them as a training data set, and we test our model on the Uniklinik Ulm study data. And so the data sets we're using, you can see them here real quick. we have two training data sets. One is the COVID-X data set, which is from one. It's one of the biggest ones with over 2,000 positive images. And we are just using our synthetic images as a second training data set on top. So we put 10,000 images that we synthetically create in the positive and negative class. We also have a validation data set that comes with COVID-X. That's also already in the paper, which is fixed. And then we have our study data as a test data set in the end. And this has one additional benefit, and this is we can get estimation of the generalization capabilities of the network, because we have actually a distributional shift between our images and the openly available ones that come from all over the world, have different radiations, different machinery used to get the images, and so we can see if the model is actually able to generalize well to this local source hospital data. Okay, so for our architecture that we use, we're using two things, of course. The first one is a classification model, which classifies the images. And I would like to tell you that we use something very fancy here, and trust me, I tried. But actually, what worked very well is ResNet 50 pre-trained. And we use some tricks, but it's mostly pretty standard. So that was a very, very robust model in this case. And the generative model that we use, which is much more interesting, is a StyleGAN version 1. And we use differential augmentation with it. And this is from a very well-written paper from last year from MIT. And differential augmentation is an awesome thing here because it works very well on small amounts of data. So this makes training the GAN actually possible. Without it, it doesn't work. I can show you some images later on if you like to. But we are using differential augmentation, and it means the images are augmented, and it means not only the real images are augmented, but the fake ones as well. And they are not only augmented for the discriminator, which is usually being done, but also for the generator as well. And this is a pretty good system, and it works really well here. Okay, how does the training progress look like for these generated images? The StyleGAN is a progressive growing of GANs variant, so we are growing the images by resolution in steps. So we are starting with a very small resolution, which you can see on the left side. And actually you can see that also the colors don't match in the beginning of the training because the model has no clue what an X-ray looks like, right? So after some training, you can see even the 8x8 images, they resemble closely small X-ray images. So we can see that this takes form, and in the end, we stopped at 256 by 256 resolution, and they looked quite good. So what does it mean? They look quite good. Of course, we evaluated this with the FID score, which is a distance measure to compare to image distributions, and we get around 100 here. And this is actually a little worse than you would like to have it. So we checked the FID score on a larger data set, and then we get around 40. So 40 is around in line with current research to this problem. So you can see with the small amount of images, we do have some drawbacks here, which is the FID. But all in all, it still works very well, despite having only about 100 images per class. And also, we have the luxury of asking radiologists to this problem because it's a cooperation. So we asked the radiologists to check some of our sampled generated images, and they said, well, most of them look really good, so we cannot really distinguish the difference between real and fake here, but some of them look really bad. And I know this because even I can see it. So I can see that about every 15th image, something like that, really doesn't look that well. And this is some strange behavior because most of them look fine, but then you have some that just don't. And yeah. Okay, so what are the results of our actual classification now? I know this is a huge table, and I wouldn't want you to focus only on the top part for now, which is the validation data. Those are those 200 images that come with the COVID-X data set. And I want you to look at this model. This is the COVIDNet, which was proposed in the paper from Wang. And you can see in metrics when you compare this to our models on top, the COVID-X and the COVID-X plus synth, that we are actually quite in line with the original model here. So that gives us a lot of confidence that our model actually does something useful here. And now I want you to focus on the bottom part, on the testing data, which is the Uniklinik Ulm data. And here we have the synthetic model compared to the non-synthetically enhanced model. And you can see that the synthetic model pretty much outperforms the other model in almost every metric that we compare to. And this is especially true for some metrics like the recall, which was very bad for the original model. We had only like 0.76 here, and that's not what we want to have in a medical setting, right? You want a really high recall if you can. So in conclusion, we can say that the classification can be improved significantly with using the synthetic images, and we can see that they reduce the distributional shift between the training and testing data here. Although we need to ask ourselves if this is just a rebalancing effect of some sort, and of course it kind of is, but that's also like one of the advantages of using those synthetic images. We can just rebalance them, right? And data leakage is another big question mark, because when you are generating the synthetic images, that's being done here on the study data from the Uniklinik Ulm. So you might have some data leakage. The generator doesn't really see, as you know, the real data distribution. It only gets the feedback. So this is something that that could be kept in mind and could be further researched. So I want to end this presentation with some more images of synthetically created X-rays, and I think they actually look very nice. And you can take a look at them, and I thank you very much for your attention.